All right, in today's lesson, let's take a look at section 4.5b, which is solving polynomial equations. And so what does it mean to solve a polynomial equation? And how are we going to do that? Haven't we been doing it? Well, you have. Most of the time so far in these polynomial equations, they have been able to be factored and you're able to solve them out. Well, today we're going to be using this rational root theorem because these polynomials that we're looking at are not easily factored. And so how do you do it? It's pretty simple. What you're going to do is take the coefficient. So if we have our equation here, f of x, and it shows a sub n x to the whatever power, which would be the degree of the polynomial, the coefficient right here, this will represent q. A sub 0 right here will represent p. And a sub 0 represents the coefficient, or sorry, the constant of the polynomial, which would be a number. And all you do is you take p over q to find the possible solutions of the polynomial. I've added a little note here, and you're going to want to make sure you add this to your notes. It says that the rational root theorem is used as a starting point for finding solutions of polynomial equations. It only lists the possible solutions, and you must test the possible solutions to find the actual solution. So it's important right here to realize that through it all, when you do P over Q, you're going to have so many different possibilities depending on the problem and the factors. And to figure out if those possibilities is actual solution, there is some extra work that must be done in order for you to find your answer there. So let's put it all together in a bit as we take a look at the irrational conjugates theorem. Now, the irrational conjugates theorem is going to be used when you have an irrational number, for example, like the square root of 5, something that you just won't get a nice number. And we're going to go ahead and learn how to take your conjugate or your 0, because what these are will end up being zeros. And we're going to come up with our equation right here in the end, or a polynomial. So we'll come back to this in our lesson, and let's go ahead and move on. So since we did all of this right here, 1 through 10, we're going to go ahead and move on down to number 11. So the problem states, according to the rational root theorem, which is not a possible solution of the equation. Well, how do you do that? Let's figure out, well, what are all the possible equations or solutions? Remember the constant right here, that'll represent p. The coefficient of the degree of the polynomial will represent q. So I'm going to go ahead over here. I'll write down the 7, and let's list all the different factors of 7. Luckily, there aren't that many. It's 1 and 2. Let's list all the different factors of 2. 1 and 2. So pretty easy. Let me fix this right here. That should be a 7. So now what I'm going to go ahead and do is this. We'll use our equation, P over Q, and start listing all the different possibilities. I'll start with this 1, and I'll put it over 1. And to make things even more complicated or give us more options, we've got to put plus or minus 1. Okay, so so far we have 2 possible solutions. We're going to go ahead next. I want to take P and use 1 and put that over 2. So I've got plus or minus 1/2. We've exhausted all the possibilities with 1 being our numerator. So then let's go to the number 7. And so from here, let's go ahead and put 7 over 1. And then don't forget, plus or minus. And then the last possibility is going to be plus or minus 7 over 2. We want 7 over 1 right here, and then 7 over 2 for the last part. So you can see we have You think that there's 4 possibilities at first sight, but because it's plus or minus, we double that, and now we have 8 possibilities. Are all of these solutions? No. These are only possible solutions. So let's go through our list right here. And I've got plus or minus 1 as a possible solution. That number's not even there, so we're not going to worry about that. Next up, we got ourselves plus or minus 1/2. Well, I see 0.5, that's the same as 1/2. That is a possible solution. Remember, we are trying to figure out what is not a possible solution. We've got plus or minus 7. 7 is on the list. No bueno. All right, so we cancel that out. We've got ourselves next up, plus or minus 7/2. That is 3.5. And I see 3.5 right here. So we have the number 2 all by itself, and that is not a possible solution of the equation. So that right there is step 1 to our adventure of finding possible or finding solutions. So number 12 puts it all together. Okay, let's try this again. So we have right here 48. Remember, that's going to represent P. The coefficient to the degree of the polynomial will represent Q. The reason why I say this one's going to be complicated, because it is, because there's so many different possibilities here. For the number 48, some factors, we have 1, 2, 4, 8, or actually even before that we have 6, and then 8, then we have 12, 12 times 4, and then there's 16 times 3, so then we have 24 and 48. A lot of different possible solutions. Luckily for Q, there's only 2 possible factors right there. That's 1 and 3. So let's go through the list right here. If we go through P over Q, right, we got 1/1, so we have plus or minus 1. And then we have next up plus or minus 1/3. After that, we have, let's go to the number 2. So we have plus or minus 2/1, which is 2. Then we have plus or minus 2/3. After that, we got plus or minus 4/1, or plus or minus 4. Then we have plus or minus 4/3. And so as you can see, we have a lot of different combinations here. And I try to pick out the problems right here where you don't have so many, so you just know how to at least do the steps and to find your answers. The next one right there would be plus or after 6, it would be 6/3, right? Plus or minus 6/3, which happens to be 2. And we have 2, it repeats itself. Also, luckily, maybe you don't have to find that 2 times. That eliminates 2 possible options. And then we'll go ahead and put after that plus or minus 8. And then we have plus or minus 8/3. And then the list continues on. So when you're doing a problem like this, where do you start? You start anywhere. Start with 1. I would start with the easiest number and go from there in order to test. So the second step is to test things out. Now, we don't have the time to go through all these different possibilities, so I want to help you out right here. And so let's just say I plugged in, and I'm going to use synthetic division. And I already plugged into this top left corner. I've already plugged in plus or minus 1. I plugged in plus or minus 1/3. And the problem was I had a remainder. So remember, if you have a remainder, that means it's not a solution. So let's go ahead right here. I want to plug in -4. Let's see if that's one of my solutions. And up right here, I write my coefficients down. 3, 11, -40. And the coefficients are coming from this polynomial. -132, 48. and let's test things out. We bring down the 3. 3 times 4, negative 12. And remember right here, we are adding things up, so then I get negative 1. Negative 1 times negative 4, positive 4. Now I'm left with 36, or negative 36. Negative 36 times negative 4, a positive 144. When I add these two numbers up, I end up with a positive 12, and 12 times negative 4 is negative 48. And so guess what? We have no remainder right here. Let's rewrite our polynomial. Okay, we started with 3x to the 4th. Now we're going to go ahead and bring this down, and it'll be 3x to the 3rd. Let's put minus x squared minus 36x plus 12. Okay, so now we have ourselves a polynomial with 4 terms. So what can we do next? Well, there are several things to think about. First off, if I do have a polynomial with 4 terms, one of the ways we could solve them is by grouping. I look at this right here, and grouping doesn't look like it'll help. So what do I do now? Let's go ahead and repeat our process right here. Okay, we're going to have to repeat the process, and my magic ball tells me that one of the possible solutions happens to be, well, let's try it out. We'll try 1/3. So I want to repeat this synthetic division process right here. And I want to use these numbers. No need to use the original. Let's use the numbers right here since it's a little bit less. And let me put it right here. I'll have 1/3 in the top corner. And let's use the numbers 3, negative 1, negative 36, and 12. And let's repeat our lovely synthetic division right here. And I want to run out of space. I want to erase some of this stuff here. That's why you guys should always use paper. Make sure you follow along. So let's plug in 3, or drop down to 3. 3 times 1/3 is going to be 1. Negative 1 plus 1, 0. 0 times 1/3, 0. Negative 36 plus 0, negative 36. And negative 36 times 1/3 is negative 12. So when we add this up, wow, we got no remainder. So that means 1/3 is another solution. Let's rewrite things out. Okay, let's see. All this right here now becomes, we had x to the 3rd is what our polynomial was before. We divided it by x. We're going to drop it down. And we are now going to have 3x squared plus 0x minus 36, which in turn is the same thing as 3x squared minus 36. So now, we could repeat the process, or what we could do is, hey, this is a binomial. What happens if I set it equal to 0? Because there is no x in the middle, right? If I had an x to the first, then I wouldn't be able to do it. What you could possibly do are your options that we've been taking a look at. We could factor things out, because remember, this is technically our equation set equal to 0. You could use the quadratic formula, which you might have to do sometime. On this one, it looks like we're actually able to solve. And you're saying, what do you mean by that, Mr. Kim? Well, let's take 3x squared minus 36 equal to 0. Let's take 3x squared and add 36 to both sides. And there you go. 3x squared is equal to 36. I could divide both sides by 3 and get x squared is equal to 12. You square root both sides and x is equal to plus or minus rad 12. we could simplify this a little bit further, and we get plus or minus, let's see, 2 rad 3. Right, factors of 12, 4 and 3. I could take the square root of 4, and that's where that 2 comes from. So I have a total of 4 solutions here. Find all the zeros. I just did that. So plus or minus 2 rad 3, 1/3, and negative 4 are all of the possible zeros. Or actually, these are all the zeros. If you were to write it as a polynomial, then I would write it as x, and then we'd have to actually put plus 4 as one of them. Then we have ourselves x minus 1/3, and then we have x plus 2 rad 3, and then x minus 2 rad 3. Now, in order for us to actually work and deal with something like this, the radicals, that's where we come down to the next part of looking at that rational root theorem, which will take us to our next problem, number 13. Actually, before we go to that, so you're saying, once again, I think the biggest thing that I skipped right here was testing a bunch of different numbers. If you had this many possible solutions, you just have to actually do it. Okay, you have to test them all out. For the sake of time, I already knew which zeros worked out, and then I already plugged them in. But like I said, you're going to have to plug in plus or minus 1, plus or minus 2, to see if they work. And I already knew that they didn't work, so why go through it? All right, so like I said, I know that it could be quite tedious, but the numbers that I will choose most of the time will not be that hard. Okay, where you have like 20, 30 different possibilities. So now let's move on to number 13. It says write a polynomial function g of the last degree that has rational coefficients and a leading coefficient of 1 and the zeros of -5 and 4 plus rad 2. So they're trying to tell us, let's come up with our zeros. So if I have a leading coefficient of 1, well, we can do that. We just got to make sure at the end, and what it's saying at the end, our degree of the polynomial, it's going to be 1x to whatever power we need. So if I want to write -5 as a 0, the last thing I showed you in number 12 was pretty much how to do that. -5 as a 0 would be x, and we're going to actually have to put plus 5, right? Because if I set this equal to 0, it will equal our -5. The next part is where we use our rational conjugates, okay? Now, when I set things up, I've got x minus. Okay, I need to set this up as a binomial. And inside this binomial, I will add one of our zeros, or the second one, which is x, or 4 plus rad 2. And what the irrational roots theorem is stating, or irrational conjugates theorem, is for this. What I'm going to do now is I'm going to take and come up with the second answer, or actually the third one. And I'm going to put x minus, but this time I'm going to take the binomial and put 4 minus rad 2 in there as such. Okay? So remember the last problem, we kind of experienced that same thing on number 12, where we had two answers with the polynomial. I had the 3x, 3x squared plus, minus 36, and then we were able to solve that out and get our two solutions. And we ended up with something that looked similar to this right here. Now here's what we have to do in our next step, and it's going to deal with these two binomials. I'm going to go ahead now and regroup. What do you mean by that? I'm going to change this to x minus 4. I'll put that in parentheses, and then plus rad 2. And I'm going to have over here, once again, I've got x minus 4 in parentheses, minus rad 2. And let's go ahead and multiply these two together, sort of. Now, here's what's going to happen. If I FOIL this out, and this is the beauty of our conjugates. If I FOIL this out, the first part, let's just go ahead and multiply x minus 4 times x minus 4. I will be ending up with x minus 4 quantity squared. The outer terms and inner terms will cancel out because I have a negative rad 2 times x minus 4 and then a positive rad 2 times x minus 4. So what happens and why we always use the irrational root theorem is that the outer and inner terms when we FOIL will cancel. And so I'm not going to write that down. What happens here now is that what's rad 2 times rad 2? It's rad 4, which is going to equal 2. So we have right here minus 2. Once again, how do I get that? It's because this is going to be positive rad 2 times negative rad 2, which is negative rad 4, and negative rad 4 is equal to negative 2. And there we go. I didn't forget about the x plus 5, and you better not forget, and I'll go ahead and leave that right there. What do I do next? Let's take this x minus 4 quantity squared, okay? And let's actually expand that out. Remember, that's x minus 4 times x minus 4. If you remember your shortcuts, then this is where it'll pay off because it's a squared, and then it's going to be minus 2ab, which is 2 times negative 4 times x. So it's going to be negative 8x, and then it's going to be b squared. And that'll take us to plus 4 squared, which is 16. And then we have right here this minus 2 still there. All right. And then from there, we still have the x plus 5. And so let's go ahead. We got x plus 5 times x squared minus 8x plus 14. And the very last thing, we're not done yet. If we want to write this as a polynomial, you have to multiply the two together. And that's something you have done earlier on. And if we do this real quick, we get right here, we got like x to the third minus 8x squared plus 14x. And then we take the 5 and we multiply it all throughout. We have ourselves plus 5x squared minus 40x and then plus 70. We'll simplify this all together, combine like terms. Looks like we got x to the third minus 3x squared minus 26x plus 70. And that right there is the polynomial with these as your zeros. I know, it's too easy for you guys, right? It's going to take some practice. The tricky part right here is making sure you understand how we regroup and write and take the conjugates of these irrational roots. Okay? For the last part here, number 14. It says use the information in the graph to answer the questions. Well, what does the graph show? Remember, things that we care about in the graph are the zeros. So I see a 0 here that crosses through the x-axis. I see another 0 that does not. I look for y-intercepts, but then right here, luckily the y-intercept happens to be at the same spot as where the x crosses. So what that tells me is we have no constant. So if 0 is one of my solutions, remember, technically what I'm looking at is x minus 0. Okay. Right here, now it says, take a look at our function. I should know that because I have n values going in opposite directions, that I have myself one, it's an odd degree. The second thing right here is let's figure out, okay, if it's an odd degree, now is it positive or negative as the coefficient? Well, it's going up and down like so, then where it's negative on the left side or it's going down, then that tells me I have a positive a value or for our coefficient there, our leading coefficient. Now remember, if it touches, then that tells me that this is a repeated solution. If it just intersects, now right here, if I were to talk about, write that as a binomial, that would be x plus 6. Right? Because if I set that equal to 0, that gets me negative 6. So putting all that down, it says what are the real zeros? Okay, x is equal to 0, x is equal to negative 6. Now don't forget right here, this 0 is repeated. And how do I know? Because it touches the x-axis. It doesn't go through it, unlike the negative 6. Now it says write the cubic function in factored form. So how am I going to do that? Well, remember, if it repeats, then it has to be an odd degree. So I could take this x minus 0 and put this to the second power. And this becomes x squared. Simple as that. How about the next solution? We take that negative 6 and write as x plus 6. And there you go. F of x is equal to x squared times x plus 6. And there's your solution right here. There's the equation of our cubic function in factored form. Because if you were to go ahead and distribute, that turns into x squared plus 6x squared. Or sorry, x cubed plus 6x squared. It's a cubic function. It fits all the values of it going opposite directions. And voila, I know that at 0, it's a repeated solution because it's x squared. And there you have it. 4.5, solving polynomial equations.